In this section, we consider the motion and thermodynamics of atoms in a solid by considering them simply as masses connected to one another by springs. This leads to wave-like motion of atomic vibrations, where we call these waves phonons. We start by considering a one-dimensional chain of atoms at their equilibrium positions in a crystalline solid. The position of the atom in the x direction can be described as integer multiples of the lattice constant A. For example, the position of the rth atom at the position x sub r is r times A from the 0th atom. We will model the interatomic forces between the atoms simply as springs. When the atom vibrates, it moves off its equilibrium position with a displacement vector u sub r. Because the atoms are coupled with springs, the displacement of one atom generally pulls the atoms around it, making traveling waves. When the displacement of atoms is parallel to the direction of the wave, it is called a longitudinal wave. When the displacement of atoms is perpendicular to the direction of the wave, it is called a transverse wave. The 3 degrees of freedom to displace an atom along x, y, or z directions leads to 2 transverse waves for each longitudinal wave. Lattice vibrations can be described by waves of various wavelengths. We will use wave vector notation, where the wave vector is 2 pi over wavelength. Small wave vectors have long wavelengths, where neighboring atoms are barely stretching the spring-like bond, so the energy is low. Higher wave vectors have shorter wavelengths and higher energy. The highest wave vector possible is when neighboring atoms have completely opposite displacement, which also has the highest energy. This wave has a wave vector equal to pi over a because its wavelength is exactly 2a. We can't have wave vectors higher than this because there are no atoms in between to represent a higher wave vector. For a chain of n atoms, there will be n waves to describe the displacement of these atoms. The wave vectors for each of these waves will be between 0 and pi over a. In general, there is one phonon mode for each atom in the chain and for each of the 3 directions of motion. We can think of this as a conservation of modes like we thought of conservation of electronic states. While the phonon dispersion relation for a 3-dimensional solid can be complicated, it is instructive to derive it for the one-dimensional chain of atoms, as it gives the linear relation at low energy characteristic of phonons. We model the atom simply as masses m connected by harmonic springs using Hooke's law. The force from each spring is proportional to the spring constant beta times the displacement. Consider the atom at position r, which has moved off its equilibrium position by a vector u sub r and has stretched the spring to the left and compressed the spring to the right. The net force from the left spring is given by the difference between the displacement of the atom at r and the displacement of the atom to the left. Similarly, the force from the spring on the right will be due to the difference between the displacement of the atom on the right and the displacement of the atom at r. The resultant net force from the springs will accelerate the mass according to Newton's law, F equals ma. The acceleration of the atom at r is its mass times the second derivative of its displacement u sub r with respect to time. Next, we suppose the solution to the force balance will be wave-like motions of the atoms. The atom's displacement at r is described by a wave vector k and a frequency omega, written as an exponential with amplitude u sub k. The Newton's law of force is m times the second time derivative of the displacement, which brings down a minus omega squared from the I omega, times the original wave u sub r. The Hooke's law of force is simply beta times the displacement at r, which we need to account for the possible shift for neighboring atoms. The atom at r minus 1 has position x sub r minus a, so the displacement is the same as the displacement at r times e to the ik minus a. For the minus u sub r, we simply get a minus 1 times beta u sub r. For the u sub r plus 1, we get a positive e to the ika and another minus 1 for the u sub r. Then the e to the ika plus e to the minus ika turns into 2 cosine of ka. giving omega squared equals 2 beta over m times 1 minus cosine of Ka. Next, we replace the 1 minus cosine of Ka with a sine squared Ka over 2 using a trigonometric identity. Taking the square root gives omega is proportional to the absolute value of sine of Ka over 2. This means the energy rises linearly with wave vector for small k for waves moving to the right, k greater than 0, or left, k less than 0. This linear dispersion relation is similar to photons, which have E equals h over lambda, or h bar k, but distinct from electrons, which have a parabolic dispersion relation. Often we study phonons using the simplified Debye model for the dispersion relation. Instead of the sine Ka formula, we can describe the relationship between energy and omega as a function of k with a simple straight line with a constant slope. The slope is defined by omega over k, which is called the phase velocity. This is distinct from the group velocity, the derivative d omega dk, which describes the speed of a wave packet or energy traveling along the wave. These two velocities are always the same for long wavelengths, small k, small omega, which are called acoustic waves, where the velocity is the same as the speed of sound. The speed of sound in continuum mechanics is given by the square root of the elastic modulus over the density. For the Debye model, the phase velocity omega over k is the same as the group velocity d omega dk is the same as the speed of sound, so the values can be used interchangeably. Because phonons only exist from 0 up to a maximum k vector, that means that the frequency or energy of phonons can only exist up to a maximum frequency or energy. This maximum frequency is called the Debye frequency, or in terms of energy and measured in Kelvin, it is called the Debye temperature.